So in the first session here, what I'm going to be presenting is just a very broad overview of the software. It's going to focus a little bit on the capabilities of the code, but also some of the the development philosophy we had, why we chose some of the architectural decisions we did, and what use it could potentially be to users in the microtomography community. So would like to quickly acknowledge some of the other contributors to the code. Francesco underplayed his role a little bit. He's been very much a driving force this entire time. So moving on. I assume to this audience, I probably don't need to spend too much time motivating why we want to do microscale modeling. I also assume there are probably some students in the audience who are maybe kind of new to this field. So just to give a very quick primer on this, if we're doing any kind of macro scale modeling where we're using some kind of composite material or some kind of porous material, and you want to be able to model the entire system, you won't be able to do this numerical simulation where you're computationally resolving the actual pore structure of the full material. And typically you wouldn't want to do this anyway. It's too expensive of a simulation. So we rely on averaging techniques, homogenization techniques at the macro scale. Actually, Naji Mansour will have a little section later in the workshop talking about some of the theory behind that volume averaging. But the point being, when you do these volume average terms, you end up with effective material properties that you need to know and compute. So effective material properties being, things like porosity, effective thermal conductivity, permeability, these kind of things. And there are a number of different ways to try to get what these properties are. The first most obvious way, which has been used, since people have been doing this work, is to try to measure it experimentally. And oftentimes, the experiments can be very powerful, but they can also be expensive, and they can have limitations in terms of what range of conditions you can conduct the experiments in. And kind of complementary to that has come out recently in the last, 15 years or so, is doing modeling actually at the micro scale. And what has really made this possible is X-ray microtomography advances. So being able to get good three-dimensional images of high quality of what your material really looks like at the micro scale has allowed these kinds of simulations to happen. And actually, right after this overview presentation will be a quick little primer on microtomography and kind of the state of the art of doing micro CT. So as Francesco mentioned, in 2013, he and Naji were starting to do microtomography samples of our, we were in the entry systems modeling projects. We were doing heat shield materials and wanted to develop a software that could perform simulations based on this. So that's where PuMA was born. And again, I assume to this audience, I don't really have to explain why microstructure is too important, but again, in case there are any students kind of new to the field, I generated a couple different microstructure samples here in PuMA. All of them have the same, material and the same porosity, and then I calculated the through thickness thermal conductivity, and you can see for what is kind of zoomed out at the macro scale would look like the same thing. It has the same constituents, the same porosity. You end up with extremely different effective material properties based on that microstructure. So this is what PuMA is attempting to do, is take the microstructural data and help you extract material properties from it. So or if you want to use kind of the more traditional technique of how to do a simulation based on microstructural data without using something like PuMA, or there's some other commercial codes that do similar things like Geodict, what your typical workflow would look like: you obtain your microtomography samples. You can do that in using a synchrotron tomography or Things like the Zeiss machines, which are just laboratory setups, are becoming better and better. You would go through a process of post-processing and segmentation of these data. And then now you want to do actual numerical simulations on them. That process first involves meshing. So you would take your microtomography sample and you would try to, usually it's a very complicated structure. So probably you're going to try to generate some kind of unstructured mesh for this. There are a number of different meshing tools that can in principle do this. Gmesh being an open source tool, ANSYS has a suite of meshing tools among many others. Once you've generated this mesh, you put it into some kind of generic numerical solver. On the open source side, maybe something like OpenFOAM. On the commercial side, COMSOL is very powerful, ANSYS is very powerful, and you can set up whatever physics you want, set up whatever numerics you want, impose your boundary conditions, run your simulations. Let's say we're doing permeability, so maybe you're imposing a pressure gradient. You run your simulations, you then post-process these simulations, integrate your bulk quantities, and then repeat the process. So in principle, there's nothing wrong with this workflow. This will give you a good numerical solutions if you do it well, and it actually gives you a lot of flexibility and a lot of power to do whatever you want. The problem is that this is a very time-consuming effort. And it's also, each step of this requires a lot of not only domain expertise, but a lot of expertise on the specific software. So the learning curve for each of these software is very high. I mean, I've gone through this process here myself, and it takes a long time for each of these steps. Generating the mesh, I would say, tends to be the most obnoxious part when you're dealing with complex microstructures and requires really understanding one of these software. So it was kind of the obnoxiousness of this workflow that made us want to generate another option. And the whole purpose of PuMA is basically to combine these three aspects: the meshing, the numerical solvers, and the integrating and post-processing your bulk quantities, and combine it into one step that is not completely brain dead to run. You still have to have some understanding of the equations you're solving and the appropriate boundary conditions and such, but with a learning curve that is not nearly as steep as the old process. So this would be kind of the PuMA workflow. You're still obtaining your tomography samples as you would. You're doing whatever post-processing, whatever segmentation you need to do in order to make these nice, clean, separable tomography samples. And then you run your various PuMA simulations in order to compute your effective material properties, and then repeat for however many samples that you have. So before getting too much into what PuMA is, I want to talk about what PuMA is not. And what PuMA is not is first an advanced segmentation or processing tool. So you can do some segmentation and you can do some processing in PuMA. I mean, of course, we can do simple things. We can crop domains, we can filter domains, and we can do simple thresholding-based segmentation. And I'll get into more what I mean by segmentation a little bit later in the hands-on section if you're not familiar. But it doesn't do some of the more advanced segmentation techniques or some of the more complex filtering algorithms. So some materials you can use simple thresholding based segmentation and get a pretty good result. Sometimes you can't. So if, for example, now a lot of the harder tomographies to segment are moving towards a deep learning approach. So you get training data on your segmentation and you use deep learning in order to segment your full image. And that's implemented in Dragonfly, which we use quite regularly. And then also, I believe a version of it is in Fiji as well. So next, what PuMA is not. PuMA is not a general purpose numerical solver. So if you want to be able to add really complex multi-physics, do simulations of I don't know, time accurate multi-physics simulations on your micro CT data, PuMA is not going to give you the tools to do that. You would have to go back to the old workflow, use OpenFOAM, COMSOL, whatever else in order to do that. It's also not an advanced visualization tool. It does provide some basic visualization, but this is not the primary focus. So we're not trying to reinvent the wheel here. We want to use the other tools that are available, and then PuMA has kind of a niche area within this world. So what PuMA actually is, what PuMA is a collection of solvers to do specific tasks. So if you've got a CT and you want to compute your permeability, you want to compute your effective thermal conductivity, you want to compute your tortuosity, your surface area, your you want to look at anisotropy of your material, these are what PuMA can do. And behind the scenes of all that, we've got a set of unifying data structures, a set of unifying linear solvers, input-output tools, this kind of thing, such that if you had another solver that you wanted to implement, and there's nothing out there in the open source or commercial world that can do it, PuMA also provides a good framework that you can build your tool on top of and take have access to a lot of the underlying data structures and solvers and stuff that PuMA utilizes. So what that actually looks like on the ground here is PuMA is kind of three separate entities. There's a C++ version, which we just call PuMA. And the C++ version works and compiles on Mac and Linux. There is a Python version, which works on Mac, Linux, or Windows. And it contains almost all the features in the C++ version. And it also contains a couple more advanced features like the permeability that is not in the C++ version. And then we've also got the graphical user interface kind of sitting in the middle. It mostly calls the C++ code, but also sometimes calls the Python PuMAPy code. And the GUI, it has most of the simple functionality in PuMA. A lot of the advanced functionality, you're going to have to use either Python scripting or call the C++ code directly. But a lot of the simple features, you want to calculate effective thermal conductivity, et cetera, you can use that in the graphical user interface, which I'll get to more in the kind of hands-on demonstration section of this. So how you actually interface with the code. There are a number of different ways to interface with it. The first is just using the PuMA GUI. So using the graphical user interface, you can, as I mentioned, use a lot of the basic functionality in PuMA. Next, calling the C++ library directly. So you can compile the C++ code as a library, and then you create a C++ project that imports that library, and then you have full access to the PuMA API. You can also import the Python package into a Python script, and then again, you have full access to now the Python API. Finally, Federico's done really great work putting this on Google Colab, particularly the Python package. So you can actually just run that directly from Google Colab on your browser if you want to, without even installing the code locally. And then finally, under development right now by the Dragonfly team, the Dragonfly software is working to implement a lot of the PuMA functionalities as plugins into their code. So for some of you, that might prove to be a really nice workflow if you're using Dragonfly to do some of your segmentation and processing. You can do their deep learning segmentation and then just go right into material properties using their GUI that then calls the PuMA software. So let's talk about some of the capabilities then of PuMA. I would put the capabilities into three main categories. We've got domain generation, material properties, and then material response. So domain generation is generating your computational domain. So we've got X-ray microtomography import. We've got woven material generation by syncing up to TechGen, which Federico will talk about more. We've got other geometry that can be generated artificially, simple shapes, also fibrous materials, sphere beds, triply periodic minimal surfaces. Next, we have material properties. So I assume this is probably why most of you are here, is you're interested in computing effective material properties. So we can do everything from just simple porosity, volume fractions, specific surface area, pore diameter, thermal conductivity and electrical conductivity, anisotropic thermal conductivity and electrical conductivity, which Federico will get into later. Also anisotropic elasticity. An important aspect anytime you're doing anisotropic simulations, and I should just quickly mention what I mean by an anisotropic simulation. So if you look at this material here on the right, you can see that this is a fibrous material. And because of that, the material properties in the direction of the fiber tend to be different than, so parallel versus perpendicular to the fibers have different properties. So if you want to simulate heat transfer here properly, you need to take that into consideration. And part of that, you have to then know how each voxel in your three-dimensional domain is oriented. So we have techniques to try to estimate from micro CT data what the orientation of your material is, assuming it's woven or assuming it's some kind of fibrous material like this. We also have simulations for tortuosity. So tortuosity is a material's resistance to diffusion. So if you put a concentration gradient across the material, how much does the kind of tortuous path of the microstructure impede the ability for these species to diffuse through? And then finally, permeability, which is probably the material property that's most important to most of you and is actually the most recent addition in our software through Federico's work with PuMA. And the permeability would be we impose a pressure gradient across the material, and we want to know how much flow rate through the material is there given this pressure gradient. So the relationship between the flow rate and the pressure gradient is the permeability. Finally, in terms of material response, I went ahead and included this. It's most of the material response is available in PuMA version 2, which actually we just checked and is not has been taken down from the NASA software catalog. We're gonna have it put back up. When we release the new version, I think they automatically took the old version down. But as part of the open source release, we're not allowed to release the microscale oxidation. So this is a tool to simulate the decomposition of the material at the microscale using a simple diffusion reaction model. That is still available in the PuMA version 2 software. You just have to go through the NASA software use authorization process. So you have to request the software. I guess they do some kind of background, and then you can have that software distributed to you. So I mentioned some of the basic transport properties that we have in PuMA here. This is just a couple demonstrations of the effective thermal conductivity on fibrous materials, the particle-based diffusion simulations we can do, some of the anisotropy we can do in order to estimate the fiber directions, and then finally permeability. Each of these we will get more into the theory, and then we will also go into actual hands-on examples of running the code. And I welcome you all to, while we're doing the hands-on examples, if you've installed PuMA already, or actually in 2 sections from now, Federico is going to go through the installation process. You should actually have enough time to install the code. It doesn't take very long to install it during that time. When we get to the hands-on, if you wanted to kind of go through it with us, I think that would probably be useful. And we can help debug any issues that people are having. Also, the microstructural material generation, just a couple examples of the things we can generate: random fiber structures, random sphere beds, some kind of foam structures, woven structures using TechGen, and then more advanced microstructural fibrous materials. So with that, I want to just briefly mention what obviously, of course, you all have the agenda, but what the agenda is really going to be focused on. It's really in 3 parts. It's in installing PuMA, running PuMA, and then we have some advanced topics at the end that may be relevant to some of your specific applications. And in running PuMA, we have that separated into the C++ and the Python versions. So for the C++, I'm going to be doing most of the tutorials for PuMA Federico is going to be taking you through how to run PuMA. So with that, I just want to open it up to any questions or just discussions. You know, most of the people, there are a lot more people on this call than we were expecting. We weren't expecting this many participants, and that's great. But what that means is we don't know most of you, so we don't know what you're working on. And it would be great to hear from some of you if you want to, I don't know, put it in the chat or something, what applications you guys are interested in, or just unmute yourself and shout out what applications you guys are interested in. We can then later on try to tailor some of our discussion towards some of those applications. So anyone has any questions or anything else, like I said, please just shout out.
So the next one will be about the primer on MicroCT. So I guess everyone can, if anyone has any questions, they can interrupt us, and I will keep monitoring the chat, and we can keep the conversation going.
Right, so we have Abhishek is mentioning fire behavior of combustible foams. That's very interesting. Damage modeling. I think Joseph and Federico, is fair to say that our capability for damage modeling, are still limited, but it's probably like an area that we will be expanding on. Is that correct?
So I think it depends on what you're talking about with damage modeling. If you're talking about, say, generating fractures and propagating fractures, that is an area we're interested in. It's an area that we don't have a lot of capabilities for right now. Unfortunately, for that kind of thing, you're probably limited to the original workflow I was talking about, where you go through the meshing process, you try to put this into COMSOL or something like that, and use some of the multi-physics they have. Now, if on the other hand, what you're interested in is samples that have already had damage, and you want to do CT scans, and then you want to look at the effect of that damage on properties, that is something you could do in PuMA. In terms of combustible foams, you may be able to reach out to me directly about the oxidation in version 2 of the software, because that may be relevant to what you're talking about there.
And also, like, there is a lot of heat transfer, right?
Yeah.
Capability that might be interesting for that application. Yeah.
So something else that I wanted to mention in terms of damage modeling is that some of the capabilities are being currently expanded in a project that is just only now starting at NASA, which basically aims at capturing MicroCT data of already damaged domains, and then investigating if with some maybe deep learning segmentation, we can automatically identify the cracks or the defects inside the MicroCT. So that's something that is starting now on my side. If I also see in the chat that somebody has mentioned plasticity modeling. So the current stress analysis that is inside PuMA, it's a linear static solver. So it works pretty well for computing effective elasticity, but for more advanced, like nonlinear behavior and plasticity, we would have to basically extend and introduce and solve the equations basically in a time fashion, which we're not currently doing. But it is something that would be really interesting, and we'll try to focus in the future.
Okay, so a couple other questions here. Can permeability of a material be modeled? So yes, Federico's working on the permeability right now in PuMA. Definitely that is our most recent capability. So it's our most it's our least I mean, I don't want to say it's not robust, but it's the least developed capability. But yes, that is currently in PuMA Pi and can be modeled. I don't know if Federico, you want to say anything else on that?
Yeah, so we have a whole section about the permeability. So I'll dive into the details of the implementation. And again, this has been a collaboration between UFF, which is a university in Brazil, and I think some of the professors are currently in the audience as well. And we basically have taken their implementation and re-implemented it inside PuMA Pi, and then we are trying to extend the solver to run on bigger domains, so that, and this is mostly because it's a finite element implementation, so it takes a very huge amount of memory in terms of once you scale the domain up. So something that we're trying to manage is basically implement a matrix-free solver, which is going to help us to scale and run the permeability on larger domains. But again, I will dive into the details a little later.
Okay, we have a question from Gerardo. How difficult is it to couple outputs like pressure gradients to some other software? So most of the time, if you're calculating something like, take permeability, for example, since you talk about pressure gradients, when you calculate permeability, of course, you're generating a number, you're generating what the permeability is, but you're also generating your pressure and velocity fields. So those pressure and velocity fields then can be outputted in some kind of VTK or usually VTK format, which can be imported into ParaView or whatever else. And I don't know exactly what formats OpenFOAM likes, but once it's in VTK, it should be easy enough to post-process it into whatever format something like OpenFOAM would want. Federico, since you did most of the structural modeling, do you want to answer the next two questions about structures?
Yeah, so I was just reading them too. So let me see. What are interactions with other calculation codes? Yeah, so for specifically with Abacus and also another finite element code called CodeAster. So we have done some cross-checking between the answers that we get with PuMA and these two software code. I actually have a couple of slides exactly about these, and so I will again wait until that specific elasticity section, which is actually at the end of my whole section, which will be probably around 1 p.m. And then the other one.
Real quick, sorry. I think if I'm understanding that correctly, they're talking about moving from a global model to the microscale model. So I think they're talking about macroscale and microscale here. So typically the way that interaction would work, it's not a direct coupling. You use the microscale to calculate, say, your effective elasticity. And then you would, in your macroscale model in Abacus or whatever else, you would input that effective elasticity as the material property that would be just an input for the volume averaged model that you're using.